Hello, welcome back for the lab. Okay, so we're gonna look now at lab 6. So this is what Marcel, Bino, and Professor Singh have prepared for today's lab. And so we have this RMD file. So essentially, it is the same kind of setup as we had in the past. There will be an RMD file. In addition to that, you also have additionally, you have the R files here that will all help you to essentially run through all the analyses that have been done during the class, and you will be able to reproduce all the analyses that were part of the class. I'm just going to quickly walk you here through the lab. So this essentially is that echo equals true, that we see the code. I talked about this in last class. Then we have the library Haven that essentially loads now read underline SPSS as a function into the function environment. So we basically have it available. You see head works already, so we see all the parameters. This is the same file that you basically used for lab 4. So this is a file that we will be using repeatedly. Again, EDU levels gives you all the EDU levels, which is 1, 2, 3, and we know that EDU is not only that. EDU is also the actual label. So we've not graduated from high school, we've graduated from high school, but not college. We've graduated from college. Then we have enhance education F as a factor. We're building the factor based on education, EDU levels, and names of EDU levels. So basically, we have this factor now. We can double check the factor always with summary. So if we do enhance, summary enhance education F, we will be able to see education F. We basically see an overview of all the different levels of education. A table will essentially show us the same things. A table summaries for factors, pretty much the same. Now we're going to go into a new folder. So most of you will remember that in last class, we basically had to subset this data file because there were some entries were missing, not only from education, where we had 6 missings. Right? We see those here. There are also additional ones missing for blood pressure, gender, and age. So this in total adds up to 821 cases. So here's the complete cases function. Complete cases essentially will reduce the number of vectors to a level. So here this is nothing else but creating CC. And CC is essentially just creating a criterion, right? So here we're false, false, true, false, true. So this creates a criterion for the overall data set for all the 4,809 cases here truncated, omitted 3,809 because it only depicts 1,000 cases. So we essentially see that we're getting a true or false criterion for all those cases where we do not have complete cases. So if we're creating now enhance sub, which results in 4,030 cases, it basically subsets it for only those where the true criterion has been met, or where a true outcome has been evaluated based on this criteria of complete cases. I encourage you to also look up complete cases and the help. So you will see this is a very useful function that basically allows for you to kind of subset according to data availability. I usually, so it would be the same as enhance sub can also be done with which is NA, and we've done that. So you have to cut from a previous lecture. So now we're running a fit of blood pressure as a function of male exact age on the subset, which essentially gives us here coefficients for male and age. So we have done that in the past. We know how to do that. We're doing now fit2. Fit2, in addition to that, also includes graduated from high school, graduated from college. Remember, with the re-level function, we can always re-level and redefine it. We have had this 2 classes, 2 labs ago. With re-level, we can redefine the reference group with ANOVA. And this is now what we did in class, where we did the likelihood ratio test. And we are getting, as a consequence of that, we're getting the association between this additional parameter, education, and our blood pressure estimate, y hat. So here we get this printout that we have seen already. Here are the regression sum of squares. We're seeing this for both models with the residual degrees of freedom of 4025. So we have 4027, 4025. We have the differences in the sum of squares between those 2 regression sum of squares. We're getting here an F based on the degrees of freedom of 3 parameters, 2 degrees of freedom. Usually it's the sample size. So this is within group degrees of freedom. Whereas this is the between group degrees of freedom, where it's 3 parameters, -1 is 2. So this is the degree of freedom here. Dividing it by the sum of squares, we're coming to the F. The sum of squares divided by the total sum of squares gets us to the F. This will, based on the F-score table, result in significant difference, meaning that education has a significant effect on blood pressure. Good. We can, for the same exercise, we can also use the LM test package. So if we run library LM test and the likelihood ratio test, we're coming to the same exact result. The advantage, I think, is the versatility in terms of models it can test. I think it succeeds a little bit in terms of versatility and applications that can be performed with LM test. So again, so now we want to calculate manually the t-value, and let's record. The t-value is calculated by the beta 1 divided by the standard error, right? So we're getting your COEF table. The COEF table is essentially COEF summary fit. So COEF summary fit is essentially, we're getting this table down there, right? So we essentially, with COEF fit 1, we get all the coefficients that essentially are applicable. So with a summary, we're getting the entire table. So we're getting all this down. We're getting the standard error, which is COEF table 2, 2. Again, COEF table is here 1, 2, and 2 is now we want only male. We want to calculate this for male, for the male variable. So 2, 2, 1, 2, 1, 2 will essentially get us the male coefficient. So this male coefficient is now, that was the standard error. Now we're getting the male coefficient. This is row 2, 1, 2, column 1. So this is 3.27. And now the calculation of the t-value is male coefficient divided by the standard error is 5.99. So now let's confirm this on our actual table. This is 5.99. So this is how easy these are essentially to be calculated, and that can be done quite easily. Now, next, we're going to check for heteroskedasticity or homoskedasticity, which is one of the assumptions we have towards the model. So we have data empty cars again. We're getting head empty cars. We're again building a fit, which is here miles per gallon as a function of weight. The summary essentially shows the same coefficient as we had already in last class. We're calculating now the residuals. So the residuals can be retrieved with the residuals functions. So if we are running this function, we're basically getting here the residuals. These are the residuals for each of the respective cars. Y hat is essentially a prediction based on car type, and this is the estimate for miles per gallon. If we're plotting now fitted versus residuals, we're getting a plot that shows us essentially the residuals as a function of the y hat. So this is essentially confirming a straight line. So we're doing scatter smooth. This is, yeah, it's not that straight, but it's straight enough, right? So it quantifies. So now we can, in addition, check this with QQ norm residuals. And we can look at this QQ plot. These are the quantiles. This is the QQ plot of the sample quantiles as a function of the theoretical quantiles in a perfect world setting with no skewness at all. Further, we can depict it as a histogram and overlaying a normal distribution. This would look like this. It's not really beautifully normally distributed, but I guess substantially enough. Now we can assume linearity. We have a somewhat linear kind of flat occurrence. And can we do this with a scatter plot? We're categorizing now by age group. So the library HMISC allows us to essentially cut and use this in groups. So we're getting now groups. And we're seeing now groups where we can essentially plot this as an index. Again, we want to see a rather flat line, which we do not see. So there's an increase in terms of age, which is not surprising. Now we're looking at this as a function between BMI and age. And this is almost a U-shaped curve. So we're essentially saying a U-shaped relationship between BMI and SPB, which is not surprising because usually you would assume BMI to be a reflection of health. Of malnourished people with very low BMI, they're usually also sick people. And those with a high BMI are usually flourishing, then they're not. So then you get in the realm of very high BMI, and this is where the blood pressure crashes again. So this U-shaped relationship is actually very much what you would expect. And there's also associations between blood pressure and BMI, which are basically following pathophysiologically principles. So this was essentially all which we did in class. You can also go back to the RMD of the class file. I encourage you to run all these exercises that we did in class, as well as these that are being done. And then you will, in addition to that, you will also analyze the HELP RCT data, and you will analyze this in the form of an observational study. So essentially, you are being asked to analyze HELP RCT as an observational study. So the hypothesis is that homeless and drink amount are structurally related. So outcome 1L is the number of drinks taken or drank in the last 30 days. The study variable is homeless. So the confounders you're being asked to run by this lab, developed by Professor Sen, Marcel, and Pinot, is to essentially include these in the model. So now you are being asked to summarize outcome and study variable, use appropriate statistical methods to assess the relationship between study variable and outcome, ideally linear regression to compare with the adjusted analyses, and then use linear regression with the study variable as independent variable and outcome as dependent variable controlling for confounders. Perform residual analysis and normality check and equal variance check. So these are the things that we have done before. So please do this in lab 6, and I'm looking forward to see your solutions. All right, thanks so much. Looking forward to see your solutions. Bye-bye.